6-4, the number e, exponential functions, and logarithmic differentiation. So we'll be spending more than one day on this section. For day one, our objectives are: 1, know that f of x is equal to natural log of x and g of x is equal to e to the x are inverse functions. Objective 2, write f of x is equal to b to the x in terms of the base e. And objective 3, differentiate exponential functions with base b. Before we get started, I'd like to spend a little bit of time on objective 2. Why is it that we want to write f of x is equal to b to the x in terms of the base e? Because we've already learned that if we have f of x is equal to e to the x, the derivative of e to the x is itself. So we know that f prime of x is e to the x. So the reason why we want to write f of x is equal to b to the x in terms of the base e is if we're able to do that, we can use what we know from before to help us do objective 3, in which we will find a formula for taking the derivative with respect to x of b to the x. What is the differentiation formula for that? Doing objective 2 and using what we know from before will help us to come up with this differentiation formula for an exponential function with base b, and that will allow us to do problems for objective 3 where we want to differentiate exponential functions with base b. So let's take a look at the first objective. Know that f of x is equal to natural log of x and g of x is equal to e to the x are inverse functions. So first, let's quickly review what it means for two functions f and g to be inverses of each other. That means when you make them work in order, where one goes first and the other one follows, the second function will undo the work that was done by the first function. So whatever the original input for the first function is, the output from the second function will be the same, because it would just undo what was done by the first function. This will happen regardless of whether g goes first, as in this composition, or f goes first, as in this composition. And also, the domains and ranges of the two functions will be switched. So let's take a look at the fact that natural log of x and e to the x are inverse functions. And because they are inverse functions, this has to be true when we do the composition of f of g of x and g of f of x. So whatever the original input, the final output will be the same. So let's take a look at that. So for f of g of x, we have f of g of x, and our function g of x is e to the x, so we have f of e to the x. And what is the function f? It's the natural log of x, so now we have natural log of e to the x, and because they're inverse functions, they'll undo each other, and you just get x. Now let's do the other order of the composition. In the other order, we have g of f of x, where f of x goes first. So we have g of natural log of x, and the function g is e to the x, so we will now have e to the natural log of x. And because they are inverse functions, this composition will give us the original input. So now we want to look at how we can write f of x is equal to b to the x in terms of the base e. This is objective 2. So we refer to what we just did. We know that the natural exponential function with base e and the natural log function are inverses of each other. So we know that e to the natural log of x is x. So if I replace x with b, then I will have e to the natural log of b, but because I have a composition of inverse functions, when the input is b, the output will also be b. So how does that help us with what we're trying to do, which is to rewrite f of x is equal to b to the x in terms of the base e? We can do that now because we just saw that b is equal to e to the natural log of b. So now, for the function b to the x, I can replace the base with e to the natural log of b, and I have that raised to the x power. So in our next step, we're just going to take what we have now, and we're going to use properties of exponents to rewrite this. Observe that what we have here is the power of a power. It's like having a to the third to the second power. When you have the power of a power, you multiply the exponents, and you will get a to the sixth here. And here, when you multiply the exponents, what do you get? The exponents are natural log of b and x, so when you multiply them, you get natural log of b times x. So we have successfully rewritten our function, which is f of x is equal to b to the x, in terms of the base e. So now we have f of x is equal to b to the x is f of x is equal to e to the natural log of b times x. We haven't done any calculus yet. We've just rewritten our function using algebra. And now we're going to go ahead and use calculus to find the derivative of this function, which is of course the same as this one. And this will give us a differentiation rule for finding derivatives of exponential functions with base b, where b is greater than 0 and not equal to 1. And to do this, we're going to use what we know from before. And what we know from before is if we have f of x is equal to e to the x, f prime of x is also e to the x. And we also have something called the chain rule. The chain rule tells us how to find the derivative of a composition of two functions. We take the derivative of the outside function evaluated at the inside function and multiply by the derivative of the inside function. So that's what we have here. We have a composition of two functions. Our inside function is natural log of b times x, and our outside function is e to the x. So using the chain rule, we can now find the derivative of our function. So we take the derivative of the outside function e to the x evaluated at the inside function, and that gives us e to the natural log of b times x, and then we multiply by the derivative with respect to x of the inside function. So when we do that, this is what we have. This is the derivative with respect to x of the inside function. So how do we find this derivative with respect to x of the inside function? The inside function is natural log of b times x. Well, b is the base of our exponential function. It's a number greater than 0 and not equal to 1. But for a particular problem, it could be, for example, 5, and we would have f of x is equal to 5 to the x. So b is a fixed value. For example, 5, or it could be something else like 3, but b is fixed for a particular problem. So natural log of b is also a constant. So taking the derivative of the inside function, and the inside function is just a constant times x, is no different than doing, for example, the derivative with respect to x of 5x. What is the derivative with respect to x of 5x? It's 5. So what's the derivative with respect to x of natural log of b times x? It would just be natural log of b. And what is this? Well, go back to the pre-calculus that we did earlier. This, e to the natural log of bx, as we saw earlier, is just another way of writing b to the x. So we can take what we have here and just replace that with b to the x. So here's what we have found. If we have a function f of x is equal to b to the x, the derivative of that function is b to the x multiplied by the natural log of the base. So now let's see if we can apply this differentiation formula that we just came up with to do problems like number 1 here. Find the derivative. So when you look at number 1, the first thing you should see is that you have a product here of two differentiable functions. So you must use the product rule, And since the second function is an exponential function with base 7, you're also going to use the differentiation rule that we just came up with. So the product rule says if you have a function that's a product of two differentiable functions, the derivative may be found by using the product rule. The derivative of the first function times the second plus the first function times the derivative of the second. So we're going to use that to do number 1. So number 1, we have the product of x to the 4th and 7 to the x. So now we use the product rule to find y prime. It is the derivative of the first function times the second plus the first function times the derivative of the second. So the derivative of the first function, you find that using the power rule. So it's 4x cubed times the second function, 7 to the x, plus the first function, which is x to the 4th, multiplied by the derivative of the second function. So here's the derivative of the second function, and that's what we just learned today, how to find the derivative of an exponential function with the base b greater than 0 and not equal to 1. You take whatever your function is. I have 7 to the x, so I write 7 to the x, and multiply by the natural log of the base. Natural log of 7. The base is 7. So we've done that. And now we just need to simplify by factoring out the greatest common factor from each term that we have in our derivative. So you can see that in our derivative we have two terms separated by the plus sign. Both terms have a common factor of 7 to the x, and also both terms have at least 3 factors of x. So I have x cubed here and I have x to the 4th here, so that's 3 factors of x times 1 more, right? So we can factor out x cubed from each term as well as 7 to the x from each term. So when we do that, from the first term we're just left with 4, and from the second term we're left with 1 factor of x, so we have x, and we're left with natural log of 7. So our final answer for number 1, the derivative of y is equal to x to the 4th times 7 to the x, is right here. And we were able to find that using the product rule and the differentiation rule that we just learned today. So let's take a look at number 2 now. Our function is 5 times the natural log of e to the 4x. So 5 is a constant, so we have a constant multiple times this function, so we can use something called the constant multiple rule. So we just write the 5, and now we need to find the derivative of natural log of e to the 4x. How do you do this? One way to simplify natural log of e to the 4x is as follows. And we're going to simplify first before we do differentiation. It'll make the differentiation easier. So as we've just learned today, or as we've reviewed today, natural log of x and e to the x are inverse functions, and what you have here is a composition of these two inverse functions. So the original input for the function e to the x is 4x, and then we have e to the 4x, and then we do the inverse function, natural log, so the two functions will undo each other, and the final output will be the same as the original input, so that's equal to 4x. Another way to see the same thing is by using one of the properties of logarithms that we looked at earlier yesterday. It's called the power property. If you have the natural log of a to the r, you can write that as r times the natural log of a. So if you do it that way, and that's the way I've done it in my notes, here's what we will have. Of course, whether you do it one way or the other, you'll have the same thing. So in the first way that I just mentioned, this part here is 4x, and 5 times 4x will give you 20x, right? Another way of seeing the same thing is as follows. So we're going to use the power property of logarithms and just go ahead and take the exponent here and write it out front, and that will give us 4x times the natural log of e. What is the natural log of e? E raised to the first power will give e, so natural log of e is 1. So 4x times 1 is 4x, and we just have 5 times 4x, which is 20x. So everything that I've done right now is pre-calculus. I haven't done any calculus yet. I haven't done any differentiation. I've just been setting up for that. And now we want to find the derivative. Why is it that we did all of this pre-calculus? Because it'll make it easy for us to find the derivative. So now look at what we've done. We've taken this function and we've rewritten it in a simplified form. And the derivative of 20x with respect to x is 20, and we're done with this problem. So here we have our third problem. We have y is equal to 2 times e to the sine x. We want to find the derivative of this problem. So how do we do that? Well, first of all, recognize that 2 is a constant multiple multiplying e to the sine x. So there's something called the constant multiple rule. So you just write 2 times the derivative of e to the sine x. So now we just have to find the derivative of e to the sine x. You should recognize e to the sine x as a composition of two functions, where the inside function is sine x and the outside function is e to the x. How do you find the derivative of a composite function? You use the chain rule. So now we'll go ahead and take the derivative here by using the chain rule. And we have the chain rule here. Take the derivative of the outside function, evaluate it at the inside function, and multiply by the derivative of the inside function. So the outside function is e to the x. The derivative of e to the x is itself. Evaluate that at the inside function of sine x, and we get e to the sine x. Multiply by the derivative with respect to x of the inside function sine x, and the derivative with respect to x of sine x is cosine x, which I have right here. So I have 2 times cosine x times e to the sine x, and that is my final answer. So today we reviewed that the natural logarithmic function and the natural exponential functions are inverses of each other. And we learned a new differentiation rule for finding the derivative of an exponential function with base b. And we use that differentiation rule along with other things that we've learned before to look at some examples where we found derivatives of functions.